Hello, today I'm going to give a brief description about the MOSFET cascode amplifier. Before I start, I would like to give some review about the MOSFET amplifier in common source mode. So let's find the gain in this configuration. The gain is basically, let's say AV, which is equal to V out over V input. Or we can use another definition, which is called GM R out, right? So the MOSFET, we can analyze this circuit by using the small signal model of the MOSFET, right? The small signal model of the MOSFET, it's basically a current source, which is GM, has the value of GM VGS. So it depends on the input, VGS, and some resistance. And we take the output from the drain. Always you take the output from the drain. Let's find the gain in this state, right? So the gain is the output voltage divided by the input voltage. By using basic circuit analysis, we can see that V output is equal to minus GM VGS times R0, right? The current times the resistance. What is VGS? VGS is equal to VG minus VS, right? What is VG? It is V input. Let's say this is V input. So it's equal to V input, and VS is 0. So we left with V input. So V output equal minus GM V input times R0. By dividing by V input, V0 times divided by V input equal to minus GM R0. Let's use another definition, which is GM R out. What is GM? GM is the transconductance of the circuit, and R out is the output resistance. GM is equal to the output current divided by the input voltage when we short circuit the output. All right? So let's do it. We short circuit and we measure the current, which is I0. So, all right. If we can look here, we can see that this resistance is no longer affecting. So the current will ignore this resistance. So I0 is equal to minus GM VGS. VGS is the same as V input. So I0 divided by V input, it is nothing but GM. R out, we can see from this here that the only resistance, which is R out, is equal to R0. AV GM R out minus GM R0. All right, why do we do this thing? Let's say that GM is about 1 milliampere per volt, right? And R0 about 50 kilo ohms. The gain of this circuit becomes what? 50 volt per volt, right? All right, that's a good gain. Why do we need more gain? Let's say that this input is about 1 microvolt, right? And we want to amplify this signal. The 50 volts is not enough because it will become 50 microvolt, right? So it's still so small. So we need to increase the gain of the MOSFET or the amplifier. How do we do this increasing? By using the terminology which is called cascode amplifier. What is the MOSFET cascode amplifier? The MOSFET cascode is basically a multiple of MOSFETs that are on top of each other. The MOSFET that has the input signal is a common source, and the other is common gate. Usually we refer to the input MOSFET as the rail device, and the one that is cascoded we call cascoded or cascode device. All right. So let's find the gain in this in this state. It's just using the small signal model again. Now this is the first transistor and this is the second transistor. All right, let's find again AV, which is equal to GM R out, right? What is GM? GM, this short circuit, this is minus GM. What is R out? Let's find R out. Now, if it is not obvious how we can find the R out, we just use the basic, which is just applying V test at the output and measure the current. This is V test. And we just measure I test, IT, let's say. So the R out is VT divided by IT. Also, when we use this analysis, we short circuit or turn off or kill any other source. So this source here becomes 0. Now, because this signal is 0, and this one depends on this one, right? So this also is not in the circuit anymore. This is GM, VGS 2, right? And this is GM, VGS 1. So this is 0 and this is 0. So let's just use at node, let's say 1, at node 1, just use nodal analysis. We can say that minus IT plus GM VGS plus V0. Now V0 is the same as VT, right? Let's just use VT minus. Let's refer to this voltage here as Vx minus Vx over RO2, right? It's equal to 0. All right. Now, what is VGS? VGS is VG minus VS. This is G, and this is S, right? G is 0, and S is X, Vx. So minus IT plus GM. This is now minus Vx, right? Plus, let's say VT over RO2 minus Vx over RO2. It's equal to 0. Now, we only need, in this equation, VT and IT. So we need to remove this Vx. What is Vx? Vx, now this is IT, and they somehow split out the current, and then this is IT right here, right? IT, so Vx is equal IT times RO1. Just substitute in the equation, minus IT, minus GM, IT, RO1, plus VT over RO2, minus IT, RO1, which is equal to 0. Let's take IT as a common factor, minus IT, 1 plus GM, RO1 plus RO1. Is R1? Yes, R1. GM, VGS, VX, right, minus RO, yeah, right. Oh yeah, this is RO2. All right. So plus RO2. RO1 divided by RO2. Right. Plus VT over RO2. So VT by IT, this is nothing but RO2 plus RO1 plus GM RO1 RO2. Right, so which is it? This one is the this one is the R output, right? So of course this is GM2, right? We refer to this one, and this is GM1. So the gain AV is nothing but minus GM1 times RO1 plus RO2 plus GM2 RO1 RO2. Now in this situation we can ignore this resistances here because they are so small. They are so small comparing to this term here, so we'll just minus GM1 GM2 RO1 RO2 SAV. Right. Now let's use the same numbers. GM is equal 1 milliamps per volt. RO is equal 50 kilo ohms. So now AV is about 2,500. So if I increase the gain so much by using only one additional MOSFET, right? So that's why we use the cascode amplifier, because it gives us so much gain comparing to only the basic MOSFET amplifier. Let's see another example here. Now, as you can see, now there are more than two inputs, more than two MOSFETs, right? Now, from here you can see that there are two types of MOSFET, which are NMOS and PMOS. The NMOS and PMOS, right? Now, because we are taking the output, we always have to take the output voltage from the drain. So this is the drain of the NMOS, of the PMOS, sorry. Yeah, the NMOS and the PMOS. The same example. First, we have to find GM. Now we can analyze this circuit without using the small signal model. GM is just minus GM1, the one that has the input signal, right? R out. Now remember, when we use the AC analysis, we always short circuit the DC voltage, right? So this VDD becomes ground. So from this node, we can clearly see that this part here is parallel with this part here, right? So let's say this is RO1, this is RO2, right? So R out is just RO1 parallel with RO2. Let's find either one separately. RO1, you can see it's the same as before, right? It's nothing but GM2, RO1, RO2. Of course, you can use the exact. And RO2, what is RO2? It's nothing but RO3, right? There's only resistance here. There is no cascoding. So R out is equal to GM2, RO1, RO2 parallel with RO3. The gain, AV, is equal to minus GM1 times GM2, RO1, RO2 with RO3. That's it. That's how we find the gain of this the cascode analysis. Now, the last example here, we have two MOSFETs, two PMOS and two NMOS. Now this is the cascode, right? This one is the cascoding MOSFET. The same thing, AV is equal to GM R out, GM minus GM1. R out, we can look from either sides, RO1, RO2. So RO1 is parallel with RO2. What is RO1? Now look at them separately. This is RO1, right? So it's nothing but GM2, RO1, RO2. And RO2, like this one, this is ground, right? So it is GM3, RO3, RO4. So AV, it is minus GM1 times GM2 RO1 RO2 parallel with GM3 RO3 RO4. All right, that's nice and all good. Is there any advantage of any other advantages than other than increasing the gain? Of course. So there are also other advantage of the Cascode, which is other than increasing the gain, it also increases the slew rate. So the response of the voltage becomes faster. Also, it becomes more stable. The circuit become more stable, and many other advantages. Is there any disadvantage? Yeah, there is one, or there are some of them. The basic one, which is one of the disadvantages, it is that because we are using so many of MOSFETs, we need high supply voltage. Sorry. We need a high voltage so we can bias all these transistors. And that's it. Thank you.